This is our 7th class, and the 7th class we are going to discuss about the ICH, the input output controller. We will see this is very important chip, and it will be more detailed. So we will discuss about the various input voltages, the various output signals, how to check ICH in this class. In the previous class we have covered up to from CPU to GMCH to RAM power supply, and also the practical aspects also. So in this class we are going to start with the ICH. So let's start with the block diagram of ICH. This is the block diagram of ICH. The 5 important input signals and the 3 important output signals. Supply, then I always say that 3 things are required for any chip: supply, reset and clock. So supply is there, then RSM reset, this is the reset signal for the ICH, clock signal from clock generator, and from all regulators power 3.3 volts, power OK signal, and from CPU supply we get power, that is VRM power, and the 3 output signals: CPU power to CPU, PLT reset 3.3 volt and PCI reset 3.3 volt. We can make how to measure these output signals, we'll see in the circuit diagram. So let's go back to our schematic diagram of DV2000. This is ICH 8. Similarly we'll have ICH 9, ICH 10, and later on PCH. Now the boards are coming up with PCH. So this ICH 8 is divided into 4 parts: 18, 19, 20, 21 in this schematic diagram. So let's start with the 18. I always discuss that the last pages will describe of the power supply of any chip. So let's go back to the page number 18. Let me first discuss about the various buses present over here, because we have to be knowledge of these buses, the connection of these buses. DMI, the direct media interface, as we have discussed in the GMCH classes, this is the only connection present between the board, that is between the GMCH and the ICH. DMI, direct media interface. Similarly, there is one more kind of bus, is PCI bus. This is PCI, not PCI Express. PCI Express is point-to-point connection. This is parallel connection. LCI is a special kind of connection between the ICH to this LAN ICs. LCI, that is LAN Connect Interface. This ICH 8 has all the functionality. It has got LAN functionality also, it has got the audio functionality also, but to enhance this capability we use these kind of chips. So drivers, when we talk of driver, what are drivers? Drivers are for loading the functionality of these chips, these LAN chips, these audio chips, these card reader chips. Modem and this audio. So what is LAN in hardware? The LAN is what is driver? Driver is for enhancing the capability, loading the capabilities of the chips present onto the motherboard, because this ICH 8 has already this functionality, but these are used for enhancing those functionalities. Okay, so this is LCI, LAN Connect Interface Connect, between LAN chip to ICH 8. Second, this is PCI Express 1. PCI Express 1 means 4 wires, 4 connections, 2 for transmitting, 2 for receiving. Similarly, PCI Express 1 and USB 2.0. We'll check what are the connections present in USB. This is LPC. LPC connection is between ICH 8 to IO chip. LPC, low pin count bus. This is present between the ICH 8 and your IO controller chip. And similarly, some more connections are there, the PATA connections and SATA connections, USB 2.0 connections. We'll see all these type of connection in this schematic diagram. So let's start with the page number 18. Page number 18. This is U32. Here the important this part represents the connection between the PCI connections. This part represents the PCI connection from AD0 to AD31. The important signals in this part is your. This is the important signals. PLT reset. What is the full form of PLT reset? PLT reset is platform reset. Platform reset. You can measure 3.3 volt over here. Just below this block diagram you see. Yes, over here. There are two signals, PLT reset and PCI reset. This is one signal, PCI underscore PLT reset, and another important signal there, PCI underscore PCI reset. As I discussed in the block diagram, here you can see in the block diagram, these are the two important signals, PLT reset, PCI reset. You can see over here in this diagram. PCI underscore PLT reset, the pin number name is PLT reset, but the signal is PCI underscore PLT reset, and the second signal is this one, PCI underscore PCI reset. Just below this diagram you will see over here, yes, this is U43A IC. This signal is fed to the U43A IC. Why this is done? This is done so as to make this PCI underscore PCI reset same as 3.3 volt. If you measure with digital multimeter, sometimes this voltage may not be 3.3 volt, but we have to make the output 3.3 volt. So we have used an AND gate over here. AND gate. This 3.3 volt input signal will go to the output if any signal is coming from here. So you can measure 3.3 volt over here across this resistor. U43A is a single IC divided in two parts in the diagram only. See over here. It's same IC, U43A, U43B. The main purpose of this IC is to make the output of PCI underscore PCI reset and PCI underscore PLT reset as 3.3 volt. Fix them at 3.3 volt. This is one IC of 14 pin and it's divided into two parts in the diagram only. So we have seen there are two important signals in this page, PCI reset and PLT reset. We can measure this signal across these registers. Okay. Let's go back to page number 19. And let's see if any more important things are there in this page. The rest is not important from the testing point, but you can obviously refer this in the data sheet of ICH 8. So we'll go back to page number 19. Here, page number 19. U32A 1 of 6. This diagram is divided into 6 portions. And let's start from RTC, real time clock. Real time clock. This is very important for feeding the real time clock present over here. The important thing is it's driven through a ICH RTC X1 through a crystal. Here you can see the crystal. See, this is the crystal. 32.768 kilohertz. This crystal is 32.768 crystal, and this is the connection ICH RTC X1, ICH RTC X2. The second important signal is ICH underscore RTC reset. This signal is fed through a CMOS battery. See over here, RTC VCC. We can see where it's coming. RTC VCC, just beside below the diagram you will see RTC VCC. See over here, RTC VCC from the CMOS battery. So if your CMOS battery is dead, then your board gets dead. So while testing the board, the first step is to remove the CMOS battery. We have to remove the CMOS battery from here. So the important signal is ICH underscore RTCX1. These two signals are fed from the crystal, and this is coming from the CMOS battery. Okay. Now the second part is LAN. I told that ICH8 has a LAN functionality also, but in the DV toothpick board there is a separate LAN IC. So all these connections are dummy. If no LAN controller IC is there, then these connections could have gone. But here these are dummy. Similarly, in the IHDA, ICH8 has audio support also, but here also these are dummy. We will refer back to these sections while covering fault-wise analysis. Like sound is not coming or your LAN is not working, then we'll come back to this section. We'll see how these are related with those problems. Here we'll cover all the important signals related to ICH. We'll come again. Now here these are SATA. ICH8 has so many SATA controllers. It has got 3 SATA controllers. See, SATA 0 RXN, RXP, SATA 0 TXN, SATA 0 TXP. 2 wires for receiving, 2 wires for transmitting. SATA 0, SATA 1, SATA 2. But in ICH8 has 3 SATA controllers. But in this board only 1 SATA is used, because you have IDE connections also. Here IDE ROM is used, IDE DVD ROM is used, and SATA hard disk is used. But your ICH8 has 3 SATA controllers. But in this DV231 board only 1 is used. So the important signals for SATA working is clock signal also. That this clock signal is coming from your clock generator IC. We'll see how, if suppose problem occurs like SATA is not working, then we have to check this signal, whether SATA signal is coming or not, whether voltages are coming to the SATA controller of ICH is not. We'll refer this back. ID, as I told, this DV231 board has ID DVD ROM. So this is going to the DVD ROM connections. IDE. LPC. This connection is from the ICH to the IO controller. ICH to the IO controller. This is the connection. This part is showing between the connection between the ICH to the IO controller. And this circle, this represents the testing point. The manufacturer has made many kind of testing point. They want to test certain things. So wherever you see this circle, this is from according to the manufacturer, this is testing point 91, testing point 92. They want to test certain things on the board after manufacturing. So they have divided this testing point. There are some set of parameters which they always want to test after manufacturing the board. Right after manufacturing the board, they want to test. This is not for repairing. This is right after the manufacturing of the board. They have to test certain parameters. So these lines, these testing points are for testing after manufacturing. And we are discussing, we are making our own testing points for repairing point of view. Okay. Now this is the CPU section. CPU section in the ICH8. I always told there is no direct connection between the direct connection means there is no bus technology between ICH8 to CPU, but CPU there is an interaction between the CPU and ICH. So this interaction takes place through system management bus. There is a signal level connection. We call it signal level connection between the CPU to the ICH. So these signals they run through SM bus, system management bus, onto your motherboard. The important signal we'll see in this part is FVRR. FVRR is one important signal. Second, CPU power good. CPU power good, that is H power good. It is fed to your CPU section. As I told, this is the last step. H power good, we have learnt in the CPU section. H power good. IGNME, this is also very important signal. Then NMI, SMI, stop clock, STP CLK, stop clock, and thermal trip. We will see what is the utility of these signals, FVRR and IGNME. These are very important signals. Similarly, NMI and SMI. Why this is required? Why these two signals are required and why this is sent through ICH? We will see. This is bit theoretical, but I will explain it simply. The FVRR and IGND, these two signals are used basically to process the floating point error. Suppose your computer is doing some floating point calculation and some floating point error gets happened because we have like 64-bit architecture, and if you feed data more than 2 to the power 64, then your processor won't be in a position to calculate the data. At that point of time, it will release a signal. So this signal processing, the FVRR and IGNME are used for processing that kind of situation. This is the legacy calculation, not present in now architecture. These are the legacy numeric coprocessor error handling. So there are two important things present, that is numeric coprocessor and interrupt controller. So whenever like your CPU gets a floating point calculation, it will transfer that calculation to the numeric processor, and at that point of time this coprocessor will release a busy signal to your CPU that I am busy with that calculation, do not feed me another calculation. See, the microprocessor and the numeric coprocessor, they interact through these bits. So while this numeric coprocessor is processing the data, it will generate a busy signal, and when it gets error, it will feed that error to the interrupt controller. That interrupt controller will release the interrupt, and that will let the CPU to know what to do, and it will clear the busy signal. This is in the legacy numeric coprocessor handling. But in now architecture, we have this kind of architecture. If CPU gets any kind of error, this FVRR signal is representing this signal, error signal. So FVRR signal is sent to the ICH and IGNME signal is sent to the CPU. It's written FVRR is asserted in the event of a floating point execution error, and IGNME, it reset the floating point unit within the CPU for DOS compatible error handling. So this IGNME is this portion. So in the newer kind of board, we have this kind of facility. In more recent kind of board, you have PCH. So FVRR and IGNME, these are fed from the PCH only. There is no GMCH, so it's directly fed to the CPU. We'll go back over here. So we have learned the important signal in this part is FVRR, IGNME, CPU power good, you can measure this at the CPU socket. There is no way, till now we haven't find any way to measure this voltage, that is FE because it's just present below the BGH and just present below the CPU. So no point we have found out what voltage exactly, but it would be roughly around 1.08 voltage. According to me, it would be roughly around 1.08 voltage, because the maximum voltage maximum signal voltage as I have seen is 3.3 volt. So it will be approximately 1.08 voltage. This is ID connection. So we'll go back to the page number 20. In page number 90, what important things we have covered? This is the RTC. Every testing starts with RTC. You have to remove the CMOS battery. This is ICH. It's fed through a crystal. ICH RTC X1, ICH RTC X2. In the second GLAN, as I told, ICH 8 has LAN capability also, but here it's dummy because there are LAN controller ICs also. Similarly, these are the audio section. ICH 8 has 3 SATA controllers, but here only one SATA controller is used. Here ID DVD ROM is used, and it has important sections. CPU section is also present over here. CPU sections means CPU controller section. CPU controller section in the ICH, and the important signal is CPU power good, that is H power good. You can measure this at CPU socket. FERR, IGNNE, NMI, SMI. What is NMI? NMI is non-maskable interrupt, and SMI is system maskable interrupt. NMI is non-maskable interrupt. There are two kinds of interrupt. One is maskable interrupt and another is non-maskable interrupt. To briefly understand this, you can take an example of printing. Suppose you give a printing command to your printer, and suppose you give 100 copies of printing, and printer gets finished, and it gives return signal to the CPU that I have got this work finished, but CPU will not take that action immediately. If suppose CPU is doing something, it will not transfer it request to the printer. But there are some kind of action where the CPU immediately transfer, and that scenario is your floating point execution. There it's a NMI, non-maskable interrupt. The CPU immediately transfer its position to that request. So that is non-maskable interrupt. We will go to the page number 20. This page is very important, very important, because here you will find many important signals. This is the SMB, system management bus. This is the SMB controller present in the ICH. SMB controller present in the ICH. It is fed through 3.3 volt. If 3.3 volt is not present, then SMB controller and ICH won't work, and if it doesn't work, then all the signal communication between the CPU and ICH will get stopped, because this is the system management bus controller present in the ICH. So the important signal is SMB data, and this is fed through 3.3 volt. And next is, there are many important signals also present here in the system GPIO, system general purpose input output. This section is present in many kind of BGA chip. So this is system general purpose input output. The important signals here is, there are many important signals. System reset, SYS underscore reset, system reset is there. Then you have VRM power good. This is very important. VRM power good. VRM power good. This is coming from the CPU and the CPU voltage, CPU regulators. CPU regulator. You can measure the voltage across this resistor. VRM power good. There are many important signals there, that BMBG, that is called bus master BG. If this signal get reset, if this signal get reset, then your bus master, whatever things SMB, like SM bus, whatever things are there in your bus, it will get reset. If this signal is reset, that is bus master BG. Okay, and system reset is also there, but the important signal from the testing point of view is VRM power load, because you can measure only this signal over here, VRM power load in this section. And in the next section there, GPIO, general purpose input output. This connection is between the new card. Here you can see new card reset. These are, we'll discuss when we'll see the fault, like your new card is not working, then we'll go back over here. If this signal won't come, new card reset, then your new card won't work. So there are more important signals present over here. Miscellaneous speaker signal. So if this signal is not present, then your laptop speaker won't work. So we'll check according to the fault wise analysis. Now the important portion is SATA clock signal. This is the ICH clock signal. 48M ICH. This signal is necessary for your USB working. This signal, this is coming from the 3, that is clock generator. Clock signal. As I told, any chip requires the clock reset and supply. So these signals are coming from your clock generator. Now the important signal, SLPS3, SLPS4, SLPS5. What these things are? SLPS3, SLPS4, SLPS5. These are ACPI management, advanced configuration power interface management built onto the hardware. There are two kind of ACPI. ACPI built onto your hardware and ACPI built onto your software, into your operating system. We call them OSPM, operating system power compatible. That is OSPM. So when SLPS4 signal comes, then all the memory controller, they get their respective voltages, and when SLPS3 comes, then all section onto your boards get the voltage. And SLPS5, here it's got dummy, because S5 state will get enabled from the IO chip. This is dummy. In some kind of board you will find it not dummy. So the S5 state will start from ICH in those kind of board. But here in this DB2000 Intel board, S5 state will start from the IO chip. We will discuss what these states are. Right now briefly I am explaining. S4 is the state when all your memory controller get their supply. S3 is a state when all portion on your motherboard gets supply. And S5 is a state after G3 mechanical off. When you press the power button in this board, S5 state will start when S5 enable signal will come from IO chip after pressing the power button. Another signal is power OK. Power OK. As I shown to you the first block diagram, these are the important signal. Power OK. Power good volt signal from all regulator 3.3 volt. This is the important signals. Power OK. And deep sleeper. Deep sleeper means, see, there are many terminology. Deep sleeper, sleep. These states are built in the ICH in order to manage right ACPI, in order to have more power efficiency. Like when your system is not using it, enters the deep sleeper. This ICH will generate a signal and the CPU will enter into the deep sleep state. Then signal battery low. Battery low. When your battery low, this signal comes. Battery low. Then power button. This signal comes from the ICH. This is very important signal. When you press the power button, this signal will go to 0. And this comes to the ICH. After this signal comes to the ICH, then it will generate signal S4. It will go into the S4 state. The S5 and power, when you press power button, this signal will come to the ICH. It will then generate S4. It will go into the S4 state. Similarly, land reset. Land reset. This PLT reset is coming to the land reset for waking up land. RSM reset 3.3 volt. RSM reset. This signal is again coming from page number 31. That is page of IO controller. So when you press the power button, two signal will come. S5 enable and RSM reset. RSM reset and power button, RSM reset signal will come. This is the reset signal of this IC. Reset signal of this IC. RSM reset and this signal. Power button. Then these two signal comes, it will generate sleep S4. It will go into the S4 state. Clock power good. This is very important signal. Clock power good. When this signal is generated, then clock generator will become active. It will then generate the clock signal. Clock power good. This is going to the page number 3. As I told, the first chip to start is IO, then ICH, GMCH, CPU, clock generator. This signal is given to the clock generator IC. We will discuss in the clock generator. We will see how the clock generator block diagram is. What is the block diagram of clock generator? In the block diagram of clock generator, we will see this is very important input signal to the clock generator IC. And again, important signal is V-gate power good. V-gate power good. As you can see over here, V-gate power good. So we have checked over here all the important input signal. RSM reset 3.3 volt, power okay, V-gate power good, clock signal from clock end and the supply, and the output signal is PLT reset, PCI reset, and CPU power good 3.3 volt. And this is the important signal we have already discussed. Clock power good, clock power okay. This is coming from the all voltage regulators. Power button, power okay. Sleep SLPS3, SLPS4. So these are the important. We will now move to page number 21. Page number 21. As I say, the last page of any block, last page of any chip will present the power. What are the important power required to operate a chip? This ICH, it requires many kind of voltages. The first one is RTC VCC. RTC VCC generated through the CMOS battery. Okay, RTC VCC. Then again, this is voltage 1D5 AGP, that is 1.5 volt is required for the operation of AGP, accelerated graphic processor. AGP 1.5 volt. We have seen 1. Again here 1.5 volt SATA PLL for the operation of the SATA connection. If this volt is missing, then no SATA controller will work. So when we get an error like your SATA hard disk is not working, then this is the starting point. This is the starting point. First we have to check whether this SATA controller in the ICH is getting this supply or not. So here we can check. Here we can check 1.5 volt across this inductor. 1.5 volt. Coil also we call it coil. This is generally inductor. Similarly for your USB, see USB. If it doesn't get 1.5 volt S0, then your USB won't work. USB core 1.5 volt. 1.5 volt is necessary for the working of USB. Similarly for the LAN, there is a voltage 1.5 volt. So if your LAN is not working, we have to check whether the LAN controller portion in the ICH is getting voltages or not. Then again 3.35 S0. So these are all the important voltages which is required for the working of the ICH. Now we'll see this voltage. VCC sus 3. This is very important voltage. 3D3 S5. 3D3 S5. VCC sus 3.3 voltage. The first voltages that is required for the operation of ICH is 3.3 volt S5. That is, after pressing power button it will get 3.3 volt. S5 means after pressing power button here in DV2000. So after pressing power button, this 3.3 volt is generated from the regulators when they get signals RSM reset and power rocket. 3.3 volt. This is also called dual voltage. In some schematic it's written dual voltage. So this is the starting point. This is the starting point of ICH. We have to check whether the ICH is getting 3D3S5 or not. This is VCC sus 1.4. These two are implemented in later kind of boards. This VCC sus 1.5 volt, this is required for the LAN wake up and the USB. Right now in this board, USB will get a start after pressing power button. But in later kind of board, the USB will start right after attaching the adapter. So this is one VCC sus 1.5 volt, VCC sus 1.5, 1, 2. One for LAN, second for USB. That is the special functionality there, wake up LAN. So this wake up LAN is implemented in the hardware like this. So these are the important voltages we have discussed. We'll again revise from page number 19. We'll see what important things are there in ICH. We'll go back to page number 1 first. ICH. Your ICH 8 is in DV2, 18, 19, 20, 21. So we have discussed all these 4 pages. ICH is divided into 4 parts in diagram. ICH is connected to various chips through different kind of buses. There different kind of buses means LCI, that is LAN connect interface, the connection between ICH to the LAN controller IC. Similarly, your PCI Express 1 connection between the ICH and mini card, and LPC low pin count connection between the ICH to the IO chip, and SATA and PATA connection. So page number 18, we'll again revise this because this is very important IC. Page number 18, we discussed this portion is representing the connection, PCI connection. Here there are 2 important voltages, PCI reset and PLT reset. PCI reset is this, PCI reset and PLT reset. We can measure these 2 signals over here. Over here, see U43A PCI reset. Why this IC is there? In order to generate 3.3 voltage at this PCI reset. You can measure this PCI reset at pin number 22 of mini connector, and PLT reset. Similarly, TLT reset. See, 3.3 volt at pin number 22 of mini connector signifies 2 things. I will discuss this when I go into the clock generator. If 3.3 volt is present at pin number 22, then 2 things are okay. One your ICH and another is clock generator. We will see how these 2 things are related. We can see over here also. Clock signal, and we tell that 3.3 volt is present and mini connector 22 number pin. It means that 2 things are good, your ICH and clock generator. And if this RSM reset supply and all these things are coming, and even though 3.3 volt is not coming, then the problem lies with the clock generator. We'll check how clock generator is faulty. So these are the two important signals. We'll go back, we'll quickly go to page number 19. This is the RTC, the real-time clock, the first starting point of any testing. This is fed through a crystal. Your ICH requires one crystal, your IO requires one crystal. Because they start before clock generator. That's why. Similarly, the important signals in this portion is, these are not important. Here, ICH 8 has 3 SATA controllers, but here 2 are dummy, 1 is used because ID DVD ROM is used. Okay. This is basically showing RTC VCC from the CMOS battery, BAT 1.1. This is the CMOS battery connection, and again we'll go. Yeah, in the CPU section we have the important signal which we can measure is H power good. FERR, H power good, IGNV, FERR and IGNV are used to design the floating point error capability, and NMI, SMI, NMI non-maskable interrupt, SMI system management interrupt. So this is the important signal in this page. We will go back to the page number 20. Page number 20. This is very important. Page number, this is the system management bus controller section of the ICH 8. If it doesn't get 3.3 volt, S5 means after pressing power button, it will get 3.3 volt. If it doesn't get, the connection between the ICH and the CPU won't happen. And in the system GPI, system general purpose input output, the important signals here is VRM power good. VRM power good, we can measure this VRM power good at this resistor. We have discussed this VRM power good. This is important input signal. So VRM power good. Rest, these are not important signal for the testing point of view. Here in this portion, power management, any power management section of any kind of BGA chip is very important. Here signal SLP S3, SLP S4, SLP S5. These are for the ACPI management. When SLP S4 is signal gets, then it enters into the S4 state. That is all memory controller get their supply. SLP S3 means all chip get their respective supply on the boards. SLP S5, this is dummy because here S5 is implemented to the IO chip. Important is power OK, power OK, power OK. You can see power OK over here. Power OK from all voltage regulators. RSM reset. RSM reset is the signal which is generated to the IO chip after pressing power button. After pressing power button, this signal goes to 0. Power button and RSM reset, they come to ICH and then ICH generates this S4 signal. Clock power OK. Clock power good. This signal is fed to the clock generator. After this signal gets to the clock generator IC, then clock generator will start. So here we have covered all the important signal. We will go to the last page. Last page. Let me see if any things I am missing over here. Okay, we will go to the last page, 21. 21, as I said, this is the last page, so it will show all the power requirement of this ICH. Power requirement. RTC VCC is the one power requirement. Second, see 1.5 volt, 1D05 S0. But the important is 3.3 sus volt. 3.3 sus volt. This is the starting point of ICH. 3.3 3D3 S5. After pressing power button, it will get this voltage. This is also called dual voltage. Dual voltage, I will describe why it's called dual voltage. VCC sus 1.5. This is implemented in later kind of boards where there is a wake up LAN or USB will start after right from the start. Here in this DV230, USB is starting after pressing power button. So these are all the voltage requirements. In the next class, we will do a lot of practicals, because in this portion I said we have got many important signals. So we will test all those important signals on the board, and in the next class after the practical we will start with the power regulation, how power is regulated onto your board, and the last thing we will cover is clock generator. So thank you for this class, and in the next class we will test this theory.